Yeah.
Yeah.
Is this working? Okay.
Yeah, nice. Hello, everyone. Welcome to the first lecture of the Machine Learning Month. A quick announcement, the lectures are not mandatory to participate in the competition itself. They're just supplementary so that you could get at least some experience into machine learning and somehow get started for the competition. Okay? With that said, we can start the lecture itself.
Right. So welcome everyone to the first lecture of Machine Learning Month. In the university, we studied a theoretical basis of machine learning, but there isn't a lot of practice in implementing it. One way to get better in any field is by practicing yourself. In FCG, we've determined that coding competitions are an excellent way to teach programming. Similarly, in machine learning, we want to use Kaggle competitions to teach us about different machine learning concepts. That's the reason we are hosting this event today, so that we can all get practical machine learning experience. When we were planning this event, we were hoping to get at least 10 participants, but right now when we counted, there are at least 30 here. So we are flabbergasted and happy for all of you, for us. Okay, so before we proceed any further, let's introduce ourselves. I am Jeremias, and my colleague is Mansur. We are second-year bachelor students studying AI, and we are part of the Fully Connected Graph. The aim of this committee is to organize events about diverse programming techniques. This is our first time organizing such an event, and we are a bit nervous. We are not experts in this field, but we hope to explain all the concepts correctly. Now let's discuss our agenda for today. Over the course of the next 4 months, there will be 3 lectures to discuss various aspects of machine learning. This lecture serves as an introduction to machine learning and data preprocessing. The second lecture will talk about natural language processing. This involves how to process textual data with linear regression and a sneak peek into the ever-popular transformer. And in the last lecture, we will cover neural networks in a practical manner. The competition ends on December 4th, and we highly encourage all of you to participate, as we believe that it will provide a valuable learning experience. We will discuss more of the competition towards the end of the lecture. Does anyone have any questions regarding the competition?
Feel free to ask your questions during the lecture. Raise your hand.
Yeah, just raise your hand.
We'll try to answer them as best as we can.
Right, I guess you all understand. So let's discuss what we will cover today. Today, we will quickly go over what is machine learning, look at the types of data and how to prepare them for processing, and finally, we will implement 4 different machine learning techniques in Python. Before we continue this lecture, we would like to gauge your understanding of machine learning. So with a raise of hands, how many of you know what machine learning is? That's great. So can someone define it? Right?
I would say it's basically teaching algorithms to learn by itself.
Yeah, that's true. So in order to get a better understanding of machine learning, let's talk about a practical problem. Suppose we are hosting a cinema website, and we wanted to find out if a movie would be appealing to a certain audience. That is, would the audience like the movie or not? Typically, we would have 3 options. 1, we can just say yes, the movie is for everyone. But this is really not solving the problem. 2, we can randomly assign a rating to the movie and hope we get lucky. This is again pointless. And 3, the smart solution is to hire a critic and ask him to evaluate the movie and come up with a report. This method is quite effective, but as our audience size increases and covers multiple different demographics, even a human can struggle to make informed decisions. Thankfully, we live in the year 2022, where data is abundant and machines can process a large amount of information. In order to solve this problem, we can look at the data of previously positive movies and train a model on them. Next, we can use this model to evaluate the rating of a new movie. This solution is intelligent and can be scaled up infinitely. It will also typically be cheaper than hiring an expert as well. So now that we have an idea of machine learning, let's discuss some formal definitions. So in machine learning, we have small x, which refers to an object and its features. There is the big X, or the capital X, which refers to all the objects in space. Next, we have y of x, which is the target or the answer of an object. And finally, we have capital Y, which refers to all the targets in the space. So machine learning can be split into multiple categories, 2 of which are supervised learning and unsupervised learning. In supervised learning, the machine is provided with label data, and it starts with labeling future items. An example is binary classification, in which we split items into two categories. Such an example is predicting whether a user will like to film, or will a person return a loan based on previous data. A slight improvement to this algorithm is multiple class classification, in which there are several class outcomes. Some examples are, what is the topic of a newspaper? Or what kind of an apple are we looking at based on its features? We also have regression, in which the target is continuous. Some examples are weather prediction, age prediction, and this is also the kind of problem that you will solve during the competition. Finally, we also have ranking algorithms. Such an example is the PageRank algorithm, which is the foundation of Google today, and can give us a solution to nearly any question. The second type of machine learning is unsupervised learning. It uses unlabeled data and finds patterns in a data set. An example would be if you wanted to find out how close certain items are to each other. So for example, suppose you had a large amount of images and you wanted to classify them based on how similar they are to each other. We can use unsupervised learning to solve this problem. With a slight improvement to the classification example, we can allow unsupervised learning to even visualize the structure of an unlabeled data set. Finally, in unsupervised learning, we can ask the model to find anomalies in the data which would not be easily seen by the human eye. Both of these types of machine learning are extremely useful. However, we will only discuss supervised learning today. Now that we are acquainted with some ML vocabulary, let's discuss data. So data is the digital gold of the modern world and can be split into multiple categories. Binary data can either be true or false. Some examples are, is this a cat? Or did the revenue increase? This can either be true or false. Typically, 1 would be true and 0 would be false. Next, we have continuous data. It can take up any real number. These can be measured on an infinite scale, and there can be infinite numbers in between the two numbers. And examples are age and the area of the apartment. We also have some examples like the number of products bought, which are strictly natural numbers. However, we will still treat these examples as continuous data. The third data type is categorical data, which can take a fixed set of finite values. These examples could be the color of eyes, like red, blue, green, yellow, whatsoever, the city, Groningen, Amsterdam, and also something like educational level. In some cases, categorical data can have an order to them. Like in the case of educational level, you could be a PhD, a bachelor, a master's, and so on. These are quite hard to deal with, and we have new models to help deal with these problems. Sometimes we also have features which have a certain order. Like for example, in the role of a movie, we can have the main actor, the secondary actor, and some background characters which aren't really that important. Then we also have the type of populated area, such as a city or a town which is much bigger, and education level, as we discussed before. The distance between these two features doesn't really make sense, so these can't be continuous. Now that we understand different types of data, let's try to classify some attributes from the competition. So what would title be? No, what kind of category would title fall under? Yeah, categorical data, that's right. The same thing with city, it's also categorical data, as well as postal code. Now what about latitude and longitude? Exactly. Now let's try to apply the same reasoning to the target feature. What would the rent be in this case? Yeah, it's continuous. Okay, so now that we have an understanding of machine learning and the data types, we can go on to data preprocessing.
Okay, so now we can move on to data preprocessing. What is data preprocessing and why do we need it? We cannot just give the data we have to the raw data we have to the machine learning model, because the machine learning model doesn't know how to know what is yes, what is no. We just have to, it can only understand 0 or 1. So, for example, we have to encode the categorical features. Sometimes there are missing values in the data set itself, so we have to account for that also. Somehow remove the missing values. Sometimes we could do it by, I don't know, putting the 0 values instead of the missing values. Or we could put the median value for continuous data. or we could somehow interpolate the values for that. And it solely depends on the problem itself. And in each case, you have to think what method do you use for covering the missing values. Also, there's a thing called data normalization. It's usually useful for linear models and maybe neural networks sometimes. Yeah. So in this lecture, we'll cover only how to handle categorical features and how do you encode them in code. So there are many ways to handle categorical features, and we'll cover one of them. It's called Hot Encoding. What it does is it changes the categorical feature into a vector where the answer that it is labeled as 1 and the rest are labeled as zeros. So an example would be if we have data column called color and we have 3 values in there, red, green, and blue, then we could encode them as shown in the table. So as you can see, the value, if the item 1 is red, we just say, okay, the red column is 1 and the rest are zeros. And if the item 2 is green, then we put 1 in that column, but not the rest. And same goes for the third item. This is nice and all, and like this helps us encode the categorical data, and that's what's done quite often when handling categorical data. One thing to mention here is that like this method is a little redundant because we can actually, if we know that there are only 3 classes in the data, for example, red, green, and blue, then we can actually remove the column red and see that if the column green has 0 and the column blue has 0, then the machine learning model can infer that it should be red. So technically, we can remove the first column and like it still will work. Okay, so now when we covered the data preprocessing, we can move on to some machine learning techniques that we will cover today. So we will cover 4 machine learning models. First one is decision trees, then we'll go to random forests, then we'll go to linear regression, and finally gradient boosting. We won't go too deep into how these methods are trained and how they produce answers. We'll just cover like the basic concepts of how they work and see what problems and like what pros and cons these models have. The first one being is decision trees. So as you can see, this is a decision tree. It answers yes or no questions, and it can give outputs for example, binary classification. Am I ready for the presentation today or not? So in the morning, I was a little bit anxious, and my presentation was made. So we go to the yes side. I was anxious, so I was not ready for the presentation, so the presentation could be canceled. Fortunately, I wasn't anxious anymore, and then I was ready for the presentation. But there could be like a different case where I didn't make the script or I didn't memorize the script, and then like the presentation definitely would be canceled because I'm not ready. But yeah, I'm ready. This is how basically decision trees look. Yep, thank you. They predict values based on if-else questions. So if this, then we go that side. If not, then we go to the other side. This can be used as for categorical data, as for continuous data also. It might sound a little weird that you can use it for continuous data because, well, you go left or right and like you have a discrete amount of answers that you can have. However, you can have the answers taken from the train set, and eventually they can generalize to many answers if you have a lot of data. All right, any questions with the decision trees? Yes?
I kind of didn't get how we can, like the last part you said about the continuous data.
Yeah. Yeah, okay. So imagine the continuous data and the in the regression problem where we handle continuous data, we can have multiple outputs, right? So we can have like the rent is like 500 euros, the rent is 400 euros, the rent is 440 euros, and so on. And so what the decision tree will have, it will have, okay, the leaf one will be 500 euros. The leaf 2 will be 400 euros, and so on. So each leaf, like the final node in the tree itself, would correspond to some continuous value. It won't correspond to all continuous values that could be, but it will account for the majority. Does it answer your question? All right. Anyone else? Okay, cool.
You have a question?
Yes?
So technically, if you have enough leaves, you can account for all values, right?
Yes, technically that is possible, but not recommended to do. So decision trees are cool, but like they have their own weaknesses. First of all, if you have a lot of branches and a lot of leaves, then that way the model could overfit the training set. What means that like it's really good only on the data it was trained on, but then later it won't generalize to like new data you were giving it. So having a huge amount of leaves, huge amount of features accounted for is actually not so good. And we will look at this also in the practical itself. How do you handle this? How do you account for the number of leaves and so on? Yeah. Next model goes random forest. Well, the decision trees are cool, but what if you have 100 decision trees? That's even cooler, because like now you can have a bunch of decision trees, they all make decisions, and then you just choose the answer that was voted for the majority. So for example, if they have a classification task, yes or no, and like is this a cat or not cat, I don't know, 51 decision trees say, okay, this is a cat, and then 49 say, this is not a cat. Then that way, the random forest will say, okay, this is a cat because the majority voted that this is a cat. And the same way they could do regression tasks. They have, each decision tree will output some value of the, for example, rent that it thinks it is, the apartment costs. And then after that, you could choose the median number or the average or like some kind of other average, and technically that could account for a good answer. All right? All right? Yes?
Having multiple decision trees mean that all of them were trained with different data? Or why else do we have it?
Yes, so how do we get multiple decision trees basically? Yes, there are like several ways you could do this. So one way is like split the data set into like the number of trees you have, and then train the trees on each specific subset of the data set itself. And then you could get like multiple trees that were trained on multiple data, and that way they will be different trees. And because they're different, they will more or less on average be good. And that's what like the voting thing accounts for.
Would the result be better on average than just using one decision tree with all of the data?
It actually depends on the problem. Sometimes like only one decision tree could be much better than having 100 decision trees. So this was something that we'll also look at in the practical itself, because you never actually know what machine learning model will work the best for the task. Sometimes you can have a decision tree with only 2 leaves and like 1 decision, and it could be like the best model that there is. But who knows? It depends on the task itself. And we will also look at how to figure that out. All right? So yeah, random forests are cool. They're resistant to overfitting because there's a lot of decision trees, and maybe some of them are overfitted, but the majority won't be. So, and like its only weakness could be that because you have 100 decision trees, it's hard to interpret. Because like a decision tree, you can just look at it and see, okay, it made this and that decision. That's why this is the outcome. But with random forest, if you have hundreds or thousands of trees, then like you cannot just inspect all of them and like say, this is the outcome it came up with. But still, there are methods how to think and look at like how the decision was made by random forest. All right? Yes?
Would that lose some accuracy if you use forest trees? Because let's say we have a data set and we split like subsections of our data on different trees.
Yeah.
But maybe some data from one tree depends on the data from another tree, and now they are not connected anymore.
Well, so how would we split the data itself? We don't actually, yeah, I'll show it on the example here. Oof. Yeah, so like, for example, this is a data set from the competition itself. How would they split it? They don't split it by columns. They split it by the rows themselves. So one row accounts for the one data point. So you have the title, the city, the postal code, and so on. And only that data is the data you use for the tree, like for some tree. And then you split then some other subset of this and train another tree on it.
Oh, okay. I thought it's the other way around.
Okay. Good that we figured it out. Okay, decision trees. Random forests. Okay, now let's go to linear regression. This is something you've probably seen already in like a statistics class maybe, or in algebra, linear algebra class. What this does basically is it tries to fit a line of best fit or a surface of best fit to the data itself. How it does it, it usually has, well, if x's are the features of an object and y is the output, then C1, C2, and Cn could be the coefficients the linear model tries to learn. And we can also rewrite this in a linear algebra form where x bold is the vector, sort of, and then here we do like a dot product. And yeah, this is like a really nice and neat notation. And we have multiple methods to how to find the solution for linear regression, and some of them also account for overfitting. But again, we won't look into those right now. Any questions? All right. Yeah, so linear regression is really sensitive to outliers, and it cannot really handle categorical values unless you encode them in one hot encoding or like some way that changes the categorical values into numerical values. It performs really well on data that is linearly separable, self-explanatory, I think, and it's yeah, it's good and all. Now let's move on to the last model for today's topic. It's gradient boosting. So an interesting idea, I think, the gradient boosting has. So imagine you have a decision tree. The decision tree somehow makes a decision, and sometimes it could be wrong, sometimes it could be right. And now what you could do is technically, you have the errors the decision tree has made, right? So you can technically train another decision tree to predict what are the errors going to be. And so that way, you can add the output of the first decision tree to the next decision tree. And that way, you'll have a model that will have its error kind of decreased a little. But then you could repeat it again. You could repeat it again, again, and again. And eventually, what will happen is, so if you look at the plot here, the first model is like the blue model. It had some error. Then that error was accounted for by the green model. And then we got a new model. But then we repeated that again, and we accounted for the errors of the green and blue model using the red model. And we can do it on and on and on to eventually get 0. But we don't actually want 0 because it will cause an overfit. Like the data or the machine learning model will be too good on the training data set. But I think you get the idea. So basically what it does, it tries to train the trees to improve it in the parts that it's bad at currently. And over time, its weaknesses are removed, and it becomes quite good at solving the tasks. It has a high accuracy, really prone to overfit. That's bad. And it is expensive to train. Well, it depends actually on the size of the data you have. If the data size is quite small, then it's actually not that hard to do. Okay. Wow. We did it in 30 minutes. Now we can move on to the practice section itself. So we have a task prepared for you, and it will be a machine learning task you will have to use Google Colab for it. Like everybody who has notebooks with them, that's nice. If you don't have a notebook, you could probably sit down with somebody else who does, and we could work together. Everybody ready? Okay, nice. So on the Google Colab, we will have a Jupyter notebook. It's basically a Python notebook, a place where you can work with Python code to execute commands and run Markdown to write comments. So first of all, to open the practice section, you have to go to the machinelearningmonths.svcover.nl, and that will redirect you to the competition link itself. And there you can find the lecture materials. Go to lecture 1, and then open the notebook itself, like open in Google Colab, and that will show you the practice section we're doing right now. Does anybody have like no access to the competition itself, maybe, or like wants a direct link to the Google Notebook? It's only you. It's all right. Yeah. Okay, so if you have set up everything correctly, what you should have is a Google Colab notebook open. It should look something like this. And in there you have already instructions pre-written by us and with some stuff written like what you have to do. So a quick overview. You're given a data set about some high schools, and what you have to do is predict if what will be the grade of the student in the final year, depending on the data that you have about them. And you have all types of data, and in here you'll download the data set, pre-process it, and eventually try to learn a machine learning for it, learn a machine model for it. In there you can also have hints, which you can open, and they can help you with the task. And yeah, that's pretty much it. In the code, we use grid search. It is something that is quite common in practice itself. So you can see if when you go to the model learning, we use grid search. It is something to a way to find the best parameters for a model. So imagine we have a decision tree, and like the decision tree has different parameters. It could have like a depth of 3, depth of 5, depth of 8. And what it does, it loops through all possible combinations of depth, max features, and eventually finds the best combination that gives you the best results. The parameters were written by us, and yeah, you can use them. Yeah, of course, if you have any questions, you can ask, and yeah, you can start.
1 hour later.
Yeah, so let's wrap things up by actually looking at the final solution and discussing the solution, right? So yeah, everybody sees. Yeah, so we download the data set and import all the necessary libraries we need. Yeah, set the random state. Some of you had the question, what do we use random state for? It's so that we can replicate our results later, so that like the randomness is random, but it's fixed. So we have the same random results every time, which kind of defeats the purpose of randomness, but like, yeah. So now we import the data just by reading the data from the data set, looking at the data by checking out the info. And now comes the part for pre-processing. So here what you had to do is list all the categories that are all the features that are featured column names that are categorical. And you could have done by just looking at the like data types, for example, it's an object, or yeah.
Well, the fact that something has numerical data doesn't really mean that it's not categorical, right?
Yes. Yeah, and in here we didn't account for some of the columns like that, and like, yeah, good that you pointed it out. So, for example, some of the columns actually had categorical data, like free time, like it was 3, 2, or 1, which technically is a categorical data. It's ranked categorical data, and yeah, we discussed it, but when I was writing the solution, I didn't account for it. But like, who else accounted for it? Good job. Yeah, so you look up the data and account for the ones that are categorical. Then what you do is you hot encode them. You just put the data inside, and then we do drop first true. It's not really necessary, but it's a nice thing to do because you decrease the dimensionality of the problem, and that way your model just will be trained on more robust data. Then what we had to do is separate the numerical data from the data itself. We just say data drop all the categorical features, and everything that should be left technically is numerical. And yeah, we can inspect it here and then like verify that it's numerical. Then we just concatenate or like join the data sets together. Then the next task was to separate the features into features and like actually target features. So our target feature was grade in year 3. And so we remove it from the features that we used for training and leave it in the target feature. All right. Then we use a Sklearn function to actually split our data set into training and test set. And of course, we mentioned the random state as fixed so that we get the same results. So now we come to the model training. Here we have 4 models we're going to train: decision trees, random forest, linear regression, and gradient boosting. The first thing we do is, like, it's not really necessary, but something I like to do is make a table of all the stuff we want to look up. So if you want to save the best parameters and see what is the score of the model on cross-validation, then it would be easy to look it up and compare. So the first concept, linear regression, it was already pre-made for you. To be honest, this code is actually a little too overcomplicated. It could have been simplified to just lr model.fit and features train, and then target train also. However, I cannot run it, sorry. But like, why I used cross-validation, it's so that we get non-biased actually metric for how the model performs on the data set itself. And yeah, that's something you just do in industry, and maybe you will encounter it later. But this is nonetheless a valid method also. And it is also applicable to the rest of the models. The next came the decision trees. Here we had a typo. I forgot the regressor, so sorry for that. Then we had the random forest. The task was just to write the random forest itself and include the random state so that the randomness is the same every time. Then came gradient boosting. It's exactly the same as we did previously. So we do a grid search, cross-validation, and then we fit the model. And then we get the results and see that, these are the best results. So finally, what we do is we look at the table and sort the values by the MSE. MSE, mean squared error, is the metric we use to compare all the models. And like the smaller the MSE, the better the model did. So in everybody's case, it should have been the linear regression performing the best. And just to keep you in mind, it's not always the case. Sometimes maybe gradient boosting does better, or random forest, or maybe decision trees. And only in this case, it came up that linear regression was the best choice. So finally, let's test the model that we got. We fit it on the training and target data. Then we predict values on the features test set. And then we compare it to the targets values. And as we can see, it's 1.8. And if we compare it to the MSEA here, it's 1.6. So it's a little overfitted, but it's fine. Now, just another thing to include is like the dummy regressor. Well, the dummy regressor is basically the thing we were talking about in the beginning, about when we were talking about machine learning. So a model that just says always the same answer. And in this case, it will try to predict the median. So say, okay, the median of the whole data. And like, just let's see how good it performs, because maybe just saying the median is already good enough. And yeah, we did it, and we saw that it's 10.6, really bad. So that means our linear regression did really good. And finally, interpretation of the model. Yeah, you can combine the coefficients of the linear regression with the labels of the model, and then sort them by the absolute value. And that way you get the list, an ordered list of features, and by how important they are for training. And yeah, that's it. Thank you for listening. And yeah, good luck on the competition. And yeah, by the way, the second lecture will be next week at Thursday from 17 to 19. It will be hosted by a PhD student in Ruch. He is a really smart dude. So yeah, come over to the lecture. It will be really fun. Thank you.